We map the equipotential lines, right? So what we've got, they've drawn them in, and they're calling them equipotential lines. Equipotential lines, a line of constant electrical elevation or voltage. So if you walk around that line, you never leave that line, you are always at the same potential. And no work is done in moving along that line. It doesn't take any work to move along an equipotential line. The electric field lines, as you saw in your lab, are always perpendicular to the equipotential lines, because that's a force in that direction, right? So you would have to be moving perpendicularly to the field lines in order not to be doing work. Does that make sense? So it says, if you were a positively charged rock with legs, would it be like, what would it be like to move along one of the equipotential lines? Try to visualize the analogy of a gravitational situation where you're walking around a mountaintop. So if you were walking around the mountaintop at a constant elevation, that's what it's like here, right? If you try to go up the hill, it's going to be hard. If you try to go down the hill, well, that's going to be easy, right? But either way, work is being done. But if you stay at the same elevation, no work is done. So that's what's happening here. And describe what it would be like to hike in the direction of the electric field line. So if you're a positive charge and you're going in the direction of the electric field line, what's that like? A rock going which way? Downhill, right? Positive charge wants to go in the direction of the field line if the force is in that direction. And opposite the direction of the field line, for a positive charge, it's like going uphill. Now, this is the tricky part. If you're a negatively charged object, it flips, right? So a negatively charged object wants to go up the hill, wants to go against the field line, right? That's the direction of the electric force on a negatively charged object, opposite the field line, and it doesn't want to go down. It would be like the other one going uphill, the positive charge going uphill. Okay. Okay. Let's turn it over, and let's take a look at these different cases here. So the first thing we want to look at So they've got these two situations. Up on top, capital Q. Down below, lowercase q. And they've sketched in some field lines for us. And they're asking us a bunch of questions about these different locations around the field lines. First thing we should do is answer number 4. Which charge is bigger? Which charge is bigger? Little q, because has more field lines coming out. And how do they compare, actually? Double? Okay. So how does the electric field at A, number 1 then. The electric field at capital A versus the electric field at little a. They're both the same distance away from the charge. Which one's bigger? Little a, because it has a bigger charge there, right? What's the electric field from a point charge? KQ over R squared. So R is the same for both. So the bigger Q has the bigger electric field at that location. And they're being tricky. They made the lowercase q a larger charge than the capital Q. Okay, what's next? How about how about 5? The electric field at capital B versus capital A. Because KQ over R squared, Q is the same for both, but R is much bigger, right, for B. So it's going to have a smaller electric field. How about number 6? The electric field at B versus the electric field at C. Equal. Same Q, same distance away, so they're equal. Number 7. Electric field at little b versus little a. It's the same as number 5, right? Okay. How about number 9? Can you do number 9? Electric field at capital A versus the electric field at lowercase b. Is that right? Oh, yeah. So the electric field at A is K capital Q over R squared. The electric field at little b is K 2Q over 4R squared. Is that right? And so what is this? This is going to be 2, and that's 16. This is 1/8. So A is 8 times bigger. Okay, so now we want to know think about electric potential, V. We use the symbol V for electric potential. Let's see, which one should we do? How about number 2? Potential difference. let's see if we can kind of reason through it, and then I'll tell you what the formula is for potential from a point charge. What do we expect? We're going from capital A to capital, between capital A and capital B. And so what are we looking at? It's the work done divided by the charge, right? If we go back up here to our, where's our equation? For there it is. One more arrow. Delta V, negative work done by the field over Q, right? So which one is the field? We're moving the same charge, let's say, between capital A and capital B that we move between lowercase a and lowercase b. The same Q is being moved. Which field is going to do more work? The one where the force is bigger. So the bigger force is going to be with the bigger field, right? Which is the lowercase q. Lowercase q is twice as much as the capital Q. So it's going to exert a larger force on a charge moving between lowercase a and lowercase b than the capital Q would exert on that force moving between a and b, right? So we have more work done going from lowercase a to lowercase b. So therefore, the delta V is going to be bigger.